So the detectors for HPLC are tabulated. There are many detectors such as absorption detectors, fluorescence detectors, electrochemical detectors, refractive index detectors, conductivity detectors, mass spectrometric detectors, Fourier transform infrared spectrometric detectors, light scattering detectors, optical activity detectors, element selective detectors, photoionization detectors, like this. These are the number of detectors which can be used and which are even commercially available, except these last three detectors: optical activity, element selective, and photoionization detector. And their mass LODs are given here, and their linear range is also given here. And there are no highly sensitive detectors as we saw for gas chromatography in case of HPLC. Such highly sensitive detectors are not found in HPLC. Of course, the absorption detectors, UV or visible absorption spectrometric detectors, are the most commonly used detectors for HPLC. Their mass LOD is 10 picogram and the linear range is from 3 to 4 decades. So the principle behind this is, if you pass a monochromatic beam of light radiation through any organic compound or any species which is having the ability to absorb that radiation of particular wavelength, the amount of light absorbed is going to be the quantitative aspect of the compound present in the sample, or the light absorbed which will be having a particular wavelength. The wavelength of the light which has been absorbed by the solute is going to decide the characteristic aspect of the solute. So the range is fixed for all those organic molecules. So what should be the range of wavelength that is going to be absorbed by the organic molecule? If the molecule is simply aromatic, what is going to be the wavelength range? If the molecule is containing unsaturated ketone groups or aldehyde groups, so what is going to be the absorption maximum? If the compound is containing more than one exocyclic double bond, what is going to be the lambda max? These are the things we have studied under UV absorption spectroscopy. So this is the principle of the absorption detector. It is going to function. Fluorescence detectors will be working based on the principle of fluorescence, molecular fluorescence. It is mainly a molecular phenomena, molecular excitation going to be taken place. When you apply energy by means of light radiation, the molecule absorbs the light radiation and it will excite to the higher energy level, and the light absorbed by the molecule is called as excitation radiation, which will have a particular wavelength that is called as excitation wavelength. Once it is excited to the higher energy level, it will come back to the ground state by emitting the light radiation. The wavelength of the light emitted is called as emission wavelength or emitted radiation. The intensity of the emission light radiation or the wavelength of the light emitted is going to be used in order to quantify or in order to identify the solute. Electrochemical detectors, mainly diffusion current detectors, are going to produce either electrical conductivity or electrical current after they undergo electrical transformation. So this is going to be the principle. While using the refractive index detectors, the difference between the refractive indices between the mobile phase and the solute in the presence of mobile phase will be measured. So absorption detectors, fluorescent detectors, and refractive index detectors are the most commonly used detectors for HPLC. Out of these three, because each and every compound will possess their own refractive indices, therefore this indicator is almost called as universal detector for LC. The universal detector for HPLC or liquid chromatography is going to be the refractive index detector, which will be having a mass LOD of 1 nanogram, highly sensitive detector, 1 nanogram. So, and the linear range of 3 decades, linear range of 3 decades. And particularly during the characterization process, online characterization process, we can use mass spectrometric detectors where an ionization chamber will be utilized in order to perform the ionization process or fragmentation process for the given molecule. Once the solutes undergo fragmentation, the M by Z values or M by Z values of the obtained ions will be recorded by means of these mass spectrometric detectors. and hence the characterization will become very simple. And IR principle, because the molecules will have their own stretching frequencies if they possess dipole moment, if they are not linear in shape, so they definitely possess IR activity. So these IR active compounds can be subjected for detection while using them as HPLC detectors. Similarly, light scattering detectors, optical activity detectors. Optical activity detectors are most commonly used in the detection of enantiomers, chiral compounds, because they rotate the plane polarized light towards either right direction or left direction. Therefore, the optical activity of the solute molecule can be measured. Similarly, element selective detectors. So these are used to detect the elements present in the solute, such as nitrogen, oxygen, sulfur, sodium, potassium, etc. So element selective detectors are these. Photoionization detectors. They measure the amount of the solute undergone ionization after getting absorbed with a light radiation. Photosensitive compounds can be measured by means of this particular detector. So let us not worry more about all these detectors. Let us concentrate on few detectors which are commonly used in HPLC. Let us take on absorption detectors. So what are absorption detectors? So these are Z-shaped flow-through cell for absorption measurements for eluents from chromatographic column. Whatever the eluent coming from the chromatographic column, they will be made to pass towards the Z-shaped flow cell, and this Z-shaped flow cell is the absorption cell into which or through which the light radiation is made to provision to pass through. So what is the amount of the light radiation pass through the species that can be measured? So in such a way the arrangement will be done. So many absorption detectors are available, and different beams of different wavelengths can be utilized, and the wavelengths of required value will be selected by means of filters. Because the interference from unwanted radiations must be avoided. Therefore, we will use filters here. There is no any much complexity there. Ultraviolet absorption detectors, UV absorption detectors. These UV absorption detectors, as you know, just like they will utilize a source made by mercury lamp, or even deuterium or tungsten filament sources can also be used. Apart from mercury lamp, deuterium or tungsten filament sources are also used. Here, the wavelength of the radiation will be fixed at 254 nanometer in most of the HPLC separations. The wavelength of the light radiation coming from either deuterium or tungsten or mercury lamp, the wavelength will be fixed at 254 nanometer, and that will be made to incident on the given compound through this particular cell. This is a cell. This is a cell which is having a path length of 0.3 to 0.321 centimeter. So this is in Z shape. As I told you, this is in Z shape. From the column, the eluent is coming out. The effluent from the column will be entering this particular flow cell, which is in Z shape, which is going to travel in this particular path, and it will exit after the detection is over. So UV source is placed along 180-degree angle to this particular path in which the solute molecule is moving. So in the horizontal direction or at 180-degree angle, UV source is glowing, and a given wavelength from the UV source is selected by means of a filter, and that radiation of particular wavelength is made to incident through the solution which is moving through the particular flow cell. And here photomultiplier tubes or phototubes or phototransmitters will be available here. They will be functioning like detectors. What is the amount of the light radiation absorbed by this species, or what is the amount of the light transmitted out from the solution will be measured, will be recorded by this detector, mainly photomultiplier tubes or photodetectors. So these two are the quartz windows. Quartz windows are given provision because if the windows are made by other materials other than quartz, they prone to interact with the UV source, UV light radiation. So in order to eliminate that problem, quartz windows are available. So they are made to be available. So why the Z shape is given to this flow cell? This is very simple. In order to increase the path length, You know Beer-Lambert's law. A is equal to epsilon Bc, where epsilon is the molar extinction coefficient, B is the path length, and C is the concentration of the solute. If the path length is increased, absorption is going to be increased. So even the negligible absorbance can be made to a extendable absorption value, acceptable absorption value, if we increase the path length of B. If we increase the path length of solution B, if we increase that, the absorption can also be increased. So the error while measuring the absorption can be minimized by simply increasing the path length of the cell. Therefore, the Z-shaped cell is going to be used in the detection of the solute molecule while using UV absorption detectors. And some UV absorption detectors are also made provision with monochromators in such a way that the required wavelengths such as 254 or 250 or 315 or 334 or 360 nanometers of wavelength can be selected by means of filters, by means of monochromators. The wavelengths employed will be 250 or 254 or 265, 315, 334 and 360 nanometers. So all these light radiations of different wavelengths can be made to be selected by means of the monochromator, and they can be made to pass through the solute which is present in the flow cell, which is moving across the flow cell, and what is the amount of the light absorbed that can be measured by means of detector. Apart from this UV absorption detectors, IR detectors can also be used because IR detectors will be functioning based on the principle that the stretching frequencies of the molecules is dependent upon the functional groups present in the molecule. So 2.5 to 14.5 micrometer or 4000 to 690 centimeter inverse is going to be the region where the instrument was discovered. So nowadays FTIR instruments are going to be used more commonly. One have the knowledge of stretching frequencies, then use of these IR detectors will become very easy. Next, fluorescence detectors. These are the most commonly used detectors for HPLC. In order to understand the principle of these fluorescence detectors, you must aware about the definition of fluorescence. I have already stated the definition of fluorescence. Fluorescence is nothing but if a molecule is fluorescent in nature, you assume you have a solute. In order to measure the fluorescent intensity, that molecule should be fluorescent in nature. This fluorescent is due to the structural property, the steric hindrance, the pH of the solution, the conjugation, a dipolar interaction, whatever it is, rigidity, structural rigidity, all these things are coming to play role while measuring the fluorescent intensity. Fluorescence is nothing but when you pass a beam of light radiation through the fluorescent molecule, the molecular excitation takes place to the higher energy level, where the molecule will not be stable. It will attain its instability and it will come back to the ground state by emitting the light radiation. This light radiation is called as fluorescent light radiation, emission radiation. The amount of the light emitted or the wavelength of the light emitted is directly proportional to the quantity or the characteristic of the solute molecule. So a simplest mercury excitation source or a xenon source is going to be employed here, so that you can see here there is a light source, and this may be a mercury or a xenon source, mercury or xenon source. So here a flow cell. Flow cell means species from the column which is entering the flow cell and it is going out as usual. This is where the detection is going to be happening. You will choose a beam of light radiation of a particular wavelength. After the absorption of that particular light radiation, the molecule which is present in the flow cell will show excitation to the higher energy level. Be able to catch me? Okay, a light source is glowing, will be illuminating, and a required beam of radiation will be selected by means of a monochromator. By means of a monochromator, this is called as excitation monochromator. So this excitation beam is required to make the molecule to excite into the higher energy level. So a beam of light radiation, here it is represented by green color. Assume green color light radiation is used here in order to show this light radiation is going to be incident on the solute molecules which are moving through the flow cell. Okay, this light radiation is made to incident on the solute molecule which are moving through this flow cell. As the light radiation is incident on the solute molecule, the solutes will show excitation to the higher energy level. The solute will show excitation to the higher energy level. Here the energy level is presented here. Sorry. Solute will excite to the energy level and it will come back to the ground state by emitting the light radiation. That light radiation is called as emission radiation. Emission radiation. That radiation is captured by a slit by means of a mirror, and that will be collected over a photomultiplier tube. Color of the light radiation here will be definitely different from color of light radiation here. Therefore, the wavelength of the excitation beam will be definitely different from the wavelength of the emission beam. Two factors you have to observe here. One is the wavelength of the emission beam and the intensity of the emission beam. The wavelength of the emission beam is characteristic to the solute, and the intensity of the emission beam at that particular wavelength is with respect to the amount of the solute present in that. Therefore, the angle between the excitation beam and the emission beam should be exactly 90 degree. Should be exactly 90 degree. Without any interferences, we can catch the emitted light radiation in a more accurate manner. In a more accurate manner, we can collect the emitted light radiation without any error. That's what the angle should be, 90 degree. Because in the molecular excitation process and the emission process, the precision and accuracy of the emission will become satisfactory when the angle between the emission beam and the excitation beam is 90 degree. So this is the principle of fluorescent detectors. Here, the fluorescent property of the solute is going to be monitored by making the molecule to be striked with an excitation beam of particular wavelength. So the molecule will show excitation to the higher energy level. It will attain instability and it will come back to the ground state by emitting the light radiation. The emitted light radiation is going to be measured by means of a photomultiplier tube. Photomultiplier tube. You will get a chromatogram. The signal is going to be amplified, and at last you are going to get a chromatogram. Fluorescent detectors are most sensitive detectors among UV absorption or other HPLC detectors, because fluorescent intensity is very high. Fluorescent intensity is highly sensitive. 10 power minus 6 to 10 power minus 9 molar is going to be the concentration of the solute what we will use in order to measure the fluorescent intensity. Therefore, they are going to be the highly sensitive detectors. Next class of detectors are going to be refractive index detectors. Refractive index detectors. Here, the refractive index is going to be the one of the properties we are going to measure after the separation of the solute molecule is over. We will take the difference between the refractive index of the mobile phase or a reference and the refractive index of the solute in the presence of mobile phase. You take water. Water will be having its own refractive index. And you mix water with glycerol. You might have performed the experiment. You mix water with glycerol. The refractive index is going to vary. So you take the difference between the refractive index of water alone and the refractive index of water glycerol mixture. That difference, that deviation, that differential refractive index value is going to be used in identifying and quantifying the solute molecule while using these refractive index detectors. This is an array of assembling components of refractive index detectors in which a compartment is getting prime importance. This is going to be the compartment. This compartment is divided into two equal halves, either diagonally or in other way. One half is to make the provision for the passing of the sample, and other half is to make the passing of the reference or the free mobile phase. Okay. A glass slab will be used in order to divide this component into two equal halves. You take a glass slab you keep it diagonally so that this compartment has been divided into two equal halves. One half is going to be followed by sample, and the other half is going to be followed by only reference. That may be mobile phase or a internal standard, whatever it is. Okay. Here is a light source. Light source may be a white light or any other typical light radiation that can be made to be monochromated by means of a lens, and it can be converted into two different radiations by means of this particular lens, and both the radiations are going to be passed between the compartment. Here the glass slab has been used now to divide the glass component. So the bending of the light radiation is going to be measured. The bending of the light radiation is going to be measured as a deflection shown by this optical device followed by a transducer. Okay. At the initial stage, only mobile phase will be moving, and both the components, both the compartments in this refractive index detector, if they are accumulated by the mobile phase, there is no change in the refractive index. Refractive index change will be zero at the initial stage. Okay. As the solute molecules are getting separated, let the mobile phase is moving in this particular direction and the solute molecules are moving in this direction. The bending of the light radiation due to the refractive index of the solute molecule, maybe definitely it will be different from the refractive index of the reference of the mobile phase. It is bending is more, here the bending is less, or here it may be more, or here it may be less, whatever it is. The extent of bending of the light radiation is due to the refractive index, because if there is only pure mobile phase is present, its refractive index will be different when compared to the refractive index of the mobile phase in the presence of the solute, because solute property is going to vary the refractive index of the mobile phase. So the deflection or the difference between the refractive index of this particular beam and this particular beam is going to be measured by means of the transducer, and this is a meter-like device, and this is utilized in order to amplify the signal, and at last we are going to record the chromatogram. You do understand? Only refractive index between the difference in refractive index between a mobile phase and the solute molecule in the presence of the mobile phase is going to be measured while using the refractive index detectors. Okay. Based on the principle of the refractive index detectors, it is very common to say that although all solutes can be subjected to measurement by using this refractive index detector, because whatever the mobile phase you're using, whether polar mobile phase or non-polar mobile phase you're using, they are going to possess their own refractive indices. So this can be called as a universal detector. That's what I told you. Refractive index is independent of the ionization or independent of the conjugation or independent of the viscosity, whatever it is. Of course, viscosity is responsible for refractive index. So this is how the refractive index is going to be used. So universal detector, this is the least sensitive, because in order to bend the light radiation, the concentration should be high, and non-ionic compounds can be monitored very easily, and the response to all analytes which are able to change the refractive index in the presence of the mobile phase. It requires separate reference flow for the mobile phase, and the absorption detectors are going to be relatively cheap when compared to refractive index detectors. Of course, refractive index detectors are going to be universal detectors. Absorption detectors are going to be cheaper. But we know the refractive index is dependent on the temperature. Therefore, it is temperature sensitive. Because HPLC, sometimes we are going to perform the operation by maintaining the temperature from ambient to at least 150 degrees Celsius. 150 degrees Celsius. Ambient means 25 degrees Celsius to 150 degrees Celsius. If you increase the temperature, the refractive indices of many solvents or many solutions will be changed. Therefore, this detector is going to be temperature sensitive. It is not going to be suitable. And they are not sensitive as most as other type of detectors. When you compare the sensitivity of these detectors with UV absorption detectors or IR spectrometric detectors or mass spectrometric detectors, these detectors are less sensitive. Next, electrochemical detector. As I told you, the electrical property of the solute molecule is going to be measured between the two electrodes either by utilizing the principle of amperometry or polarography or coulometer, conductometry. They offer advantages because most of the organic compounds and even inorganic compounds are going to be electroactive. Are going to be electroactive. The electroactivity of compounds can be monitored by means of the electrodes which is present over the detector. So you can see here, two electrodes can be used, counter electrode and working electrode and counter electrode. The effluent from the column can be made to pass through the flow cell, and the variation in the electrical conductivity or the current is measured by means of a suitable galvanometer or ammeter, or any galvanostat or potentiostat can be used to regulate the current and the potentiostat. The amount of the current generated is directly proportional to the concentration of the solute. And mass spectrometric detectors, I have already told, from the HPLC system, the solute molecule will be made to pass towards the mass analyzer. Here, the solute molecule is going to be bombarded by a high energetic beam of electron, with the solute fragmentation going to be taken place. The M/Z value of the fragmented solute is going to be measured, and that will be used to plot the chromatogram of M/Z versus the time, and that is going to be the chromatogram in case of mass spectrometric detectors. And if you look at the applications of HPLC, there are no fields are excluded from the analysis by HPLC. Pharmaceutical samples can be subjected, biochemical samples can be subjected, food samples can be subjected, industrial chemicals can be subjected, pollutants, forensic samples, and clinical samples. All variety of the samples can be subjected, particularly in pharma industry. Nowadays, RP-HPLC technique is the dawn. We can say heroic of all those separation techniques. This HPLC is in pharmaceutical industries. So many antibiotics or sedatives, steroids or analgesics can be easily subjected for separation in pharmaceutical industries by RP-HPLC and even NP-HPLC. One of the most commonly used stationary phase while using RP-HPLC is octadecylsilane. So phosphate buffers are going to be employed in order to maintain the pH up to 7.5, and water methanol acetonitrile systems are going to be employed as mobile phases, because stationary phase will be a non-polar, octadecylsilane will be a non-polar, and the mobile phase will be polar one. Therefore, we will use either water acetonitrile or methanol, or mixture of water methanol, mixture of water acetonitrile, or mixture of methanol and acetonitrile. So amino acids, proteins, carbohydrates in biochemical samples, artificial sweeteners, fragrances, I told you in the class, antioxidants, aflatoxins, and additives, all these things can be separated. So these are some typical chromatograms for the analysis of soft drink additives by using bonded phase as a stationary phase and isocratic elution with 6% acetic acid and 94% water at a flow rate of 1 ml per minute. At flow rate of 1 ml per minute. So 4 solutes have been separated in 10 minutes under this particular chromatographic condition. Bonded phase, which is a nitrile, more polar stationary phase is used. Polar stationary phase with polar nitrile bonded phase packing. HOAC and water mixture, intermediately polar. We cannot say non-polar because water is present, but the compounds have been eluted. 4 compounds have been eluted. You can look at here methyl parathion pesticides, chlordrin, zeodrin, parathion, diphonate, diazinium, EPN, ronel, trithion. All these compounds, 8 compounds have been separated in 10 minutes. These are called as organophosphate insecticides using the column of configuration 4.5 millimeter by 250 millimeter with 5 micrometer bonded phase particles. And this is going to be the mobile phase and flow rate. Like this, you can see here 30 compounds can be separated by gradient elution. So up to here one mobile phase is used, and from here to here gradient elution is performed. So within 47 minutes we can complete the elution of 30 compounds with acceptable